business traffic. Yeah, this is ahead of itself. Overall, it's pretty great. That's. Yeah. And it's also keys to them. I'll give those to you. Yes, I ran out. Okay, so this, along with packet 6 are your remaining assignments, and these are both due at the end of the school year. Both be worth 100-point quiz grades. Okay. Okay, so number one, from 5 a.m. to 10 a.m., the rate at which vehicles arrive at a certain toll plaza is given by AFT, where T is the number of hours after 5 a.m. and AFT is measured in vehicles per hour. Traffic is flowing smoothly at 5 a.m. with no vehicles waiting in line. Write but do not evaluate an integral expression that gives the total number of vehicles that arrive at the toll plaza from 6 a.m. to 10 a.m. Well, we know we have a rate. So if I want to accumulate that rate to turn that from vehicles per hour to number of vehicles, I just take the antiderivative. It's all easy. Just have to set up the integral notation without having to do anything more than that. Okay, part B, find the average value. So average value, that's average value theorem. I can apply that for this problem, 1 over B minus A. Make the calculator do the work for us. We can enter this in our calculator. Make sure you're in radian mode. This is the average value of AFT. AFT is vehicles per hour, so this will stay as vehicles per hour. Okay, so it's asking, is the rate increasing or decreasing? So rate is at the A of t level. Increasing, decreasing, this is referring to what? Is it A of t itself or something different? A prime, yeah. It's asking for what's happening at A prime of 1. If A prime of 1 is positive, we know the rate is increasing. If A prime of 1 is negative, we know it's decreasing. Well, we have our calculator, so we can make the calculator find A prime of 1 for us. Okay, this is calculator active, so we're gonna make the calculator do all the derivative work for us. What's the unit of measure gonna be? Vehicles squared up. In part D, a line forms whenever A of t is greater than or equal to 400. The number of vehicles in line at time t equals 4 is given by n of t, where A is the time in which the vehicle first begins to form to the nearest whole number. Find the greatest number of vehicle in line at toll plaza and the time interval from 8 to 4. Justify your answer. So we know this is EVT related since it's asking for absolute max. So we know with EVT, we're going to be setting our derivative equal to 0, finding our critical point, and then testing each critical point. So let's go ahead and find n prime. And prime is derivative of this expression, which means we're going to have to involve second theorem. We know these two operations cancel each other out. This is not going to change much, just the upper bound gets inserted. Okay, set equal to 0. So we can make the calculator do the work for us. Graph A of t minus 400, see where across the x-axis, and that's going to be our starting point, our critical point. Yeah, I'll let y2 hold that a of t minus 400, so I can just call this function again. 400. But I don't want to graph the first one, so I'm going to unhighlight the equal sign. My critical point is between between a and 4, so I know it's going to be greater than 4. So I'm just going to change my window here. Let's say I want to go from 1 to 5 or from 0 to 5, just so I can see around my corners here. I'm in the hundreds here, so I'm going to let my y min be a negative, let's say 100 to positive 100, to see where that looks like. I want to see some curve so I can have an easier time scrolling through. Okay, so my critical points are my x-intercepts. Okay, 1.469. Second. And 3.597. So we have our, it says the first critical point is the time when the line first begins to form. So that's our first critical point. We have a second critical point, 3.95, and then our third critical point is at 4. So we just take each of them, plug it into our NFT, and compare whichever produced the highest and lowest at values for n is going to be our absolute max or absolute min. Thanks. So just take turns inserting them all into my A value is going to be 1.469. So from 1.469 to 1.469 is still 0. 1.469 to 3.598, that'll give me 71. 1.469 to 4, that'll give me 62. So my first critical point is also my lower bound. And then we compare the three values. Highest y value is our absolute max. 71 cars. Okay, let's look at number 2. F and G is defined by f of x. You got the natural log graph. And you have the polynomial x to the fourth plus 2x cubed. Graphs of f and g are shown. One intersection is at -2, and then another intersection at x equals b, which we can find ourselves. They're not giving that to us. Find the area of that enclosed region. So they're both functions. Top minus bottom will be an easy way to set this up. But first, let's graph it and find that intersection which we need for our upper bound. Find that intersection there. Second trace, intersect 5. Pick a point close to the intersection. The other graph, pick a point close to the intersection, enter again. 0.781 or 0.782. Top minus bottom, the top is the natural log, the bottom is the polynomial. No squared, no, right, we're not doing volume here, so it's just top minus bottom is the height portion, that's the width portion, width times height, accumulate that over the course of the interval, and you have your area. Should always come out to be positive, 3.605, 3.603. Or 4, it's up to you. Force that. Third, the decimal to be 604 or 603. Part B, between -2 and B, let h be the vertical distance between the graphs of f and g. So h is just some distance between it, and if I want to find the distance, it's always top minus bottom, right? So I can just build my h of x that way. H is just some distance between f and g. So it says, is h increasing or decreasing at x equals -0.5? Well, I know that h is distance, so h prime would be the rate of change of the distance. So I can just do h prime is just f prime minus g prime. If I want to find h prime of -0.5, just plug in -0.5 in for f prime and g prime. Okay, I'll make the calculator to work for me here. So if I do 8 I got negative 0.6. Therefore, the vertical distance is decreasing at t equals negative 0.5. Okay, part C. The region enclosed by the graph of f and g is the base of a solid. Cross sections of the solids taken perpendicular to the x-axis are squares. So x-axis is this way, perpendicular is vertical, so that's nice. We can just keep the functions the way they are. So our base is just top minus bottom. We want this to be a square, so the formula for squares is base squared. And then to find the volume, we just take the integral of that region from -2 to 0.782. Make the calculator do the work for you from there on out.
On the, in there, like, no calculator FRQs.
1 and 2 will be calculator active. 3 through 6 will be non-calculators. Yeah. Okay. Part D. Vertical line in the XY plane travels from left to right along the base of a solid described in part C. Vertical line moves at a constant rate of 7 units per second. Find the rate of change of the area of the cross section. So hopefully we see this and understand that you see that time is involved a lot here. This is kind of getting us to try to connect this with related rates. Right? But we start off with the area that so it's along the base of the solid described in part C. And it says find the rate of change in the area. Well, we have the area built. So let's just let this be F and G, okay? So our area, we're always going to start off with some formula here. So this is our starting point. We want to find the rate of change of area with respect to time. So we got to now build in our time component. So A becomes what? Related rates, time is involved here. A becomes dA over dt. So we go through our whole derivative process. Here we got to go through what rule here? Chain rule, right? Okay. Outside first. Inside's derivative. Everything is getting impacted by time, so we also need a dx dt. Okay, we want to find dA dt at negative 0.5. So plug negative 0.5 in for all the f and g. And you know dx dt is dx dt is 7. Negative 0.5, you can just enter that into the original function at prime of negative 0.5. We can make the calculator find that for us. Units squared per second. Okay, let's flip over to number 6, and if we have additional time, we can always come back and do some more from 2022. But I want to hit the 3 big ones here first. So again, 1 and 2 are calculator. Number 6, 3 through 6 are non-calculator. So number 6 here, we're going to keep in mind that we're doing this without a calculator. Okay, particle P moves along the x-axis such that for time t greater than 0, position is given by x at t equals 6 minus 4e to negative 1. Sorry, 4e to negative t. Particle Q has different velocity. V of t equals 1 over t squared. So they give the position for particle P and they give the velocity for particle Q. Find the velocity of particle P at time t. So for part A, we can just do derivative to get to our velocity function for our particle P. Six goes to 0. 4e to the negative t becomes 4e to the negative t times negative 1, right? Exponent's derivative. Or you can write it as 4 over e to the t, either is fine. Yeah.
What about the negative sign?
This negative here. I multiply those together now. So reduced, yeah. Okay, find the acceleration of particle Q. Well, we know the velocity of particle Q is 1 over t squared, so I can find the derivative of that to get to my acceleration for particle Q. Let me clean this up a bit, so I don't have to go through quotient rule, I can just go through power rule. All right, so now it's asking, is the speed of this particle increasing or decreasing? So if I want to find the speed of particle Q, what do we need to do with velocity acceleration? Compare their what? Signs, yep. So I can plug in any value greater than 0. This is always going to give me positive. This is always going to give me negative. So positive and negative, what does that tell us? Decreasing speed, yep. Part C. Find the position of particle Q. Well, we only have velocity of particle Q. We can find the antiderivative, which will give us our change of position, and then plus C will show up. We can solve for C, and then we can convert that to a position function. Okay. So for velocity, take the antiderivative. So t to the negative 2, take the antiderivative, becomes t to the negative 1 over negative 1. If I go through power rule, plus C. I do have an order pair that I can work with. My order pair is 1, 2. So plug 1 in for t, 2 in for y, and solve for c. Once you solve for c, replace the c with what you found. And now we have our position function. Okay, part D, as t approaches infinity, which particle will eventually be farther from the origin? So we're looking for a position, right? So we want to compare the limits of both of the position functions. We have one that we just built, and we have one that's given to us for particle P. So we'll just do a limit as t approaches infinity for both of them, and see which one lands further away from the origin. So if I plug in infinity in for e to the t, that will go to 0, 6 minus 0, 6. Plug infinity in for t, I get that's basically 0, 0 plus 3 is 3. So particle P is going to be further from the origin since 6 is greater than 3. Okay, we have some time, so let's see if we can do some of the other 2022 FRQs. Let me see which ones do. We did 1 and 2. Part number 3. F is the differential function, f of 4 equals 3. F prime is given. Let's the F prime graph. We got a semicircle, 2 line segments. Find f of 0 and f of 5. Well, if I want to find f of 0, I know I have to involve area. Final equals initial plus displacement. I want to find f of 0, but I'm starting at f of 4 because that's what's given to me. I got to go backwards. So just understand that I know it feels like you want to go from 0 to 4, but you're starting at 4, so I got to start at 4 and go to 0. It's going to feel a little backwards in the beginning. We can always put the bounds later, but we can then adjust and change the signs. But this is your starting point here. So I want to find my position at 0, but I'm given my position at 4. So start at 4, go to 0. Now that you have that set up, you can flip the bounds. Make it minus 0 to 4. F of 4 you already know. So you just have to figure out the integral from 0 to 4 of f prime. That's just the area under the graph. And these are all nicely defined geometric shapes. So we know this is a semicircle. 1/2 pi r squared. Radius is 2. Two squared is 4. 4 over 2 is 2. Don't forget, a negative is involved because we need this to be below the x-axis. So f of 0 is just 3, which is f of 4, minus a negative 2 pi, which is 3 plus 2 pi. And this negative came from the fact that we had to put the bounds. Part B, find x coordinates of all points of inflection. Points of inflection is going to be the peaks and valleys of your f prime graph. So there's a valley at -2, sorry, at 2, and also a valley, sorry, a peak at 6. So 2 and 6. F prime changes from between increasing and decreasing. Or C. Let G be defined as f of x minus x. On what interval is G decreasing? So we just go through the first derivative test for g of x. We'll find G prime, put it onto our sign line, find critical point. So here's our g of x function. We want to find critical point. So G prime, f prime minus 1. Set G prime equal to 0. Solve for f prime equals 1. If you look on your graph, f prime of 1 is at 5 and 7. 7 is the endpoint, so the only critical point is 5. So look at your f prime. F prime minus 1 is negative. F prime minus 1 for 6 is positive. So we know decreasing on the interval from 0 to 5 because G prime is less than 0. Part D, find the absolute minimum. So again, extreme value theorem. So we want to test G of 0, G of 4, and G of 7. Right? Those are the endpoints and critical points. Oh, sorry. We're talking about G of X here. So G of 0, G of 5, and G of 7. So plug 0 into G of X, 5 into G of X, 7 into G of X, and see which one produced the highest and lowest Y values. Mornings and afternoons, I've been going through packet 6, so hopefully you guys are able to make some progress with packet 6. But in class, I'm just going to be going through the FRQs. So tomorrow I'll work on some FRQs from 2021, but hopefully you guys are able to do a little each day. And so hopefully by this weekend, you would have seen, hopefully worked through all the FRQs. You know, make a preparation for next week's AP exam. All right, go get your phones. All right. Yeah, they're all really cool. Yeah. Yeah. That's fine. Yeah. I'll show you the rest of the time more. Okay, yeah, you still with the
Yeah, the picture.
Okay, thank you.
The other, it's the last two, I think, last 6, which, yeah, the police. Yeah.
So, you know, I will be expert.
Could be 7. Which is negative 0.5, but this will still win. You're right. I made a mistake here. Should be F some minus 7.
Okay.
Yeah,
Okay.
but this is still.
Yeah, there's so many.
You're right. Yeah, that should be 7. Look at infinity. I just plugged in infinity here to imagine what would happen. I plugged infinity. So e to infinity is a really large number. 4 over infinity is 0, so that goes away. This well, it's easy because if you imagine this being infinity, a really large number of denominators, the 4 is going to be a really small fraction, which is